All right, so vitamin C example. We want to conduct a placebo-controlled experiment. That means we are going to take into account the placebo effect that determines if taking vitamin C supplements reduces the risk of getting a cold, and if sleeping more hours at night also reduces the risk of getting a cold. We want to administer 2 different doses of vitamin C, as well as having a control group that receives no vitamin C. We want to test 3 different sleeping schedules, 5 hours, 7 hours, and 9 hours. I don't think we'd want to have a control group that has no hours of sleep. That would be unhealthy. We are also concerned that gender may play a significant role in both reaction to vitamin C and sleep with respect to the chances of getting a cold. So I think gender is going to play a role in whether you get a cold and how you react to these things. We have a group of 90 men and 90 women volunteers for the study, and it'll be carried over the course of a 2-month period. All right. What is the response variable of this experiment? Whether you get a cold or not. That's what we're measuring at the end. Okay. The responses are going to be either yes, I got a cold, or no, I didn't get a cold. These would be the levels. No, levels, I'm sorry, levels are of an explanatory variable. These are just the responses. Is it qualitative or quantitative? Quantitative is numbers, so it is qualitative. We'll talk about this in chapter 1. We're getting a little ahead of ourselves here. Qualitative is synonymous with categorical. Yes, no. What are the factors? The factors are amount of vitamin C. Don't just say vitamin C. It's the amount of vitamin C you take. And it's a 2-factor experiment, the amount of sleep. What are the levels of each factor? For vitamin C, there are 3 levels, 0 milligrams, 50 milligrams, and 100 milligrams. For sleep, there are 3 levels, 5 hours, 7 hours, and 8 hours. 5, 7, and 9 hours. 9. State the treatments. So the treatments are always going to be the combinations of each of our levels. So treatment 1 would be 0 milligrams of vitamin C and 5 hours of sleep. 0 milligrams of vitamin C and 7 hours of sleep. 0 milligrams and 9 hours of sleep. Now same thing for 50, so 50 milligrams and 5, 50 milligrams and 7, 50 milligrams and 9, and the last 3 combinations, 100 milligrams and 5, 100 milligrams and 7, 100 milligrams and 9. So there's a lot of different treatments because there's 3 levels of each of the 2 factors. 3 times 3 is 9. 3 groups of 3 is 9. So 9 different levels. 9 different treatments. What are the experimental units? The 180 guys and girls, humans. Humans, it sounds funny, sorry, but whatever. Those are experimental units, all 180 of them. What variable would you block for? Well, they told us that they think gender is going to play a role, so we're going to block by gender. Why do we use blocks on this variable for this experiment? Well, it's a stupid question. Why? Because they're concerned that gender may play a significant role in both the reaction to basically just copy this down. They told us to block for gender. That's why we're going to block for it. So I'm sorry, I'm not going to copy it down. Why do we randomly assign treatments to the experimental units or subjects? To create treatment groups that are as similar as possible across the variables we can't control. That's why we do it. Give one confounding variable that may be an issue in this experiment. Can you control this variable? If so, how? If not, what aspect of your design handles that variable? So I guess we could just pick any variable we want here. Whether you live in, if we're in the winter, let's say it's wintertime and we live in Minnesota versus living in Texas. Like if it's cold outside versus if it's not cold outside, or maybe let's say job. Like if individual works outside or works inside. Maybe it's wintertime. And if you work outside, then you're outside in the cold all day. Maybe you got a better chance of getting a cold. And if you work inside, maybe you... so that's a variable that could be a problem. Can we control this variable? No, we can't really control the jobs of the subjects. So no, can't control. Sorry, I'm getting right and sloppy. If not, what aspect of our design handles this variable? The randomization and the replication. By randomizing and having enough subjects, the number of outside workers and inside workers should be balanced in all treatment groups. So if we randomly assign people, each treatment group is going to have some people that work inside and some people that work outside, so it should kind of balance out. The 4 principles of experimental design are comparison, random assignment, control, replication. How does this design address each of these? Oh my gosh, this is a huge question that I am not ready to answer. I mean, what I need to do with this problem is what I did with this starred problem up here. I'd have to do this whole crazy thing right here. And by the way, there's never been an AP test question that has asked you to describe all 4 of these things in one question. That would be like writing an essay. They usually just focus on 1 or 2 and ask you to describe how you would, address 1 or 2 of those things. So I think it would probably be a good question, but I don't want to take 20 minutes to do it, so I'm sorry. I'm going to skip it, and maybe in the future I will take it out of the notes. Using studies wisely. So a lot of this last section is just kind of common sense a little bit. So how do we interpret the results of an experiment? The real question is whether the differences we observe in the response variable are about as big as we might get from chance alone, from the randomization, from the random assignment, or whether they're bigger than you would expect to see from the random assignment. If the observed differences are bigger than we would expect from chance alone, we'll attribute the differences to the treatments. In this way, we would say that the differences are statistically significant. To say it another way, an outcome is statistically significant if the probability that it happened by chance alone is so low that we're convinced there must be another explanation, namely that the treatment caused the outcome. And if this wording is kind of sounding familiar a little bit, if the probability it happened by chance alone is so low compared to that 5%, right? It's kind of that same thing as the same setup as the discrimination in hiring example. For example, if caffeine really has no effect on pulse rates, then the average change in pulse rate of the 2 groups should be exactly the same. However, because the results will vary depending on which subjects were assigned to which group, the average change in the 2 groups will probably differ slightly. Thus, whenever we do an experiment and find a difference between the 2 groups, we need to determine if this difference is small and could be attributed to chance variation in the random assignment, or if the difference is bigger than you would expect from random assignment, and therefore is a difference due to the treatments. I feel kind of guilty that, I mean, this is a really big idea, and I'm just kind of reading it to you, and we're not doing a lot of concrete examples on it. We are going to learn how to analyze the effects of these experiments. We're going to learn how to decide if something's statistically significant or not later on in the year. For now, though, we'll just kind of do some of these thought exercises. How can we determine if the results of an experiment are statistically significant? So we do have a distracted driving activity that is an experiment. However, we may not do this in class due to time constraints. Last topic is the scope of inference, which I'll leave to the last video.